Hey guys, so today I'm going to talk about nuclear radiation, what it is, and like what happens during a nuclear decay reaction. So let's get started. What is radiation? Radiation, definition here. Radiation is particles and or energy that's emitted from any radioactive source. Essentially, you have an atom, and from the nucleus of that atom, nuclear reaction, you have a piece of that nucleus that is unstable, and so it kind of pops out of the nucleus and goes out into the world. And so those particles, or energy that those particles have, or light energy that comes out when it pops out, any of that, that's considered radiation. And it can have a dangerous effect on you, but most of the radiation, unless you get lots and lots of it, isn't really going to hurt you at all. Okay, so radiation is really more dangerous if you have lots of it rather than radiation itself being dangerous. It's kind of like water. If you have a ton of water coming at you, it's very, very dangerous. But if it's just a little bit of water, like rain, not a big deal. Okay, so what causes radiation and radioactive decay? It's unstable nuclei. So we have some isotopes of atoms that are unstable. What makes them unstable? Well, isotope has to do with the neutrons. Essentially, a neutron kind of holds the nucleus together, like it holds those protons together. Protons don't really want to be with each other. Okay, so protons are positively charged and they repel each other and they don't really want to be together. It takes neutrons in that nucleus to kind of hold those protons together like glue. So you have to have the right amount of neutrons in there, and for a lot of elements, that amount it can be several different versions. Like you can have this many neutrons, or this many, or this many, but then there are some where you don't have enough neutrons, or you have too many neutrons. So it's an unstable, to make an atom unstable, it's just the wrong ratio of protons to neutrons. It's just not stable. So when that happens, you get a piece of the nucleus that basically just breaks off from it. Okay? And hopefully the resulting piece of leftovers up here is still is stable then. If it's not, then it will also decay eventually and it'll break apart. Um, and you'll get another emitted particle. You'll get something else there. So radioactive decay, unstable nuclei, all right? So it's the wrong ratio of protons to neutrons. And then it loses energy by just spontaneously emitting a piece of itself. Okay? So where does this radiation come from? Like, where is the radiation around us? Well, honestly, there is radiation everywhere around us. It's all around you, and it's just a little bit. It's called background radiation that you have just kind of around you all the time. Your body is used to it. Okay? Don't be scared of something that's always there, because it's always been there and it's not hurting you. You're used to it. It's only when you get excessive amounts of the radiation that it might actually cause harm. So here's sort of a Venn diagram of, not a Venn diagram, a pie chart of the radiation that you're typically exposed to. So the most radiation that you're exposed to actually comes from radon. That's the most dangerous. Radon is an element, and all of it is radioactive. Radon is such a large element that all of it is unstable and it will always break apart. Radon actually is produced from the tiny amounts of uranium that is in the soil around us. So uranium in the soil around us, pieces of that uranium break off, and because pieces of the nucleus broke off, now that is no longer uranium, it can turn into radon. And that radon is a gas. So those atoms float up out of the ground as the uranium turns into radon. And so you constantly have radon kind of coming up out of the ground. And it's not really a big deal because the air just kind of takes it away and we're fine. The only time it becomes a big deal, the radon, is if you have like a basement or something else that will trap the air, you don't have very good circulation in there, then the radon can kind of build up in that basement. And so you can get a basement that's a bit more radioactive than normal. Spend a lot of time down there. We have seen some health effects from that. So a lot of houses, when they're sold, it is the law that you actually have to be tested for radon, and you should get your house tested every 10 years or so just to make sure you don't have radon building up. I actually used to own a house with a radon problem, and it's really easy fix. All you have to do is kind of increase the ventilation down there. So you just install some more ventilation to kind of get the air flowing, and then the problem's fixed. Radon won't build up. Right? Other places you might get radiation from? Medical x-rays or any other medical diagnostic thing. Internal radiation, like the food you eat, some of it is radioactive. Almost all bananas have a little bit of radioactive potassium in them. Terrestrial, that means the ground, so you're going to get some radiation from any uranium or other things that might be in the ground or in cinder blocks. Cosmic radiation, things coming out from the sun, all sorts of things. Okay, so there's radiation around you. Now, here is a chart. It is a very large chart of all the isotopes that exist. Okay, so if we take a look at this chart here, grab my mouse here. Down here on the x-axis, we have number of neutrons. Okay, so right here we have basically 0 neutrons, and as we move down, we get more and more neutrons. Right here on the the y-axis, we have number of protons. So it's a ratio of protons to neutrons, and as you go up each and every single row here, you get more and more protons. So the very first row here is 1 proton, hydrogen. Second row is 2 protons, helium. Third row is 3 protons, lithium. Okay, I'm going to zoom in just so you can see this. Hydrogen, helium, lithium, beryllium, boron, all the way up. This is the 8th row, so this is oxygen. So everything here, I'm just going to look at this oxygen row. Everything here in this oxygen row, everything here in this oxygen row has 8 protons. Now, down here on the x-axis, each of these, as you go progressively larger, gets more and more neutrons. So this one here has 4 neutrons, 5 neutrons, 6 neutrons, 7 neutrons, 8 neutrons, 9 neutrons, 10 neutrons, 11 neutrons, so on and so forth, all the way up to 20 neutrons. Now, the correct ratio of protons to neutrons for oxygen is anything here in black. These are stable, and so they're not going to break apart. That's how we kind of measure it here. Anything in black means that it doesn't break apart. So we have actually 3 isotopes of oxygen that are stable, and so 8 neutrons, 9 neutrons, and 10 neutrons. Any 8-proton atom with those amounts of neutrons will be stable, and it will exist, basically. Anything, though, that is not that will be radioactive, and it will break apart eventually. The different colors here indicate how long it takes for it to break apart, like how radioactive it is. So these light blues here, they will take somewhere around maybe a year to break apart. Okay. Anything, though, in the greens or in the reds, they break apart very, very quickly. Milliseconds or even faster. So basically they don't exist unless we make them. So these are the how radioactive things here. You can tell that we have every single element pretty much has a stable isotope until you get way up here. This is where you actually start getting elements that don't have any radioactive isotope or any stable isotopes. So let's zoom into that bigger section here. Right up here, we have uranium-238. That is a relatively stable one. You also have uranium-235, which is 765 right here. These are the ones you'll find in the ground. The 235 is fusible, so that's what they use with nuclear bombs. You also have thorium-232, which isn't quite so radioactive. It's pretty stable. But most of the elements up here, you have radioactive elements. So the element itself, like for example, if you come up here and look at number 94, number 94 is plutonium. Okay, so we're just 2 above uranium here. There is not a single isotope of plutonium that is stable. So any plutonium you have is completely radioactive. It will break apart anywhere from a year to a few seconds. Okay, so plutonium is highly radioactive, which can make it very dangerous. But all plutonium is radioactive. And in fact, it's actually everything that is after number 82. Okay, once you hit around, this is bismuth, which is number 83. Once you get past lead, this is lead right here. Bismuth has 1 stable isotope. Now we think it's somewhat unstable. It might break apart in a few million years, but it is really stable. But everything basically 83 and up doesn't really have anything that's stable. It's kind of like it's just too big to exist. So it's just so big it's going to fall apart. Okay, so 82, by the way, is lead. Lead is the largest element we have that has a lot of stable isotopes. Okay, so this is all the elements. Now, there are 3 types of radiation. Okay, 3 types of radiation. There's actually more, but these are the 3 types we're going to talk about. Alpha, beta, and gamma. All right, gamma is the most dangerous. Gamma can actually go through paper, it can go through walls, it can go through wood. The only thing that will actually stop and protect you from gamma is something like lead, a thick sheet of lead, or a thick cinder block, something made out of cement. So gamma is pretty dangerous. It is the one you want to be careful of, honestly. And nuclear reactions will emit a lot of gamma radiation. It's a big bright flash. So that's the dangerous one right there with the nuclear radiation if you're far enough away from it. That bright flash is really dangerous to you. And it can only be stopped by lead or by like cinder blocks. Okay. Beta is kind of the in-between here. And beta can basically go through paper, it can go through some thin walls or like curtains or something like that. It can even go through glass, but it will be stopped by like a drywall or by wood. So if you're behind just a basic house wall, it will protect you from large amounts of beta radiation. That will stop the beta radiation. Just stay away from the window. Alpha is the least dangerous, honestly. Alpha can be stopped by almost anything. I mean, you can put a piece of paper in front of you and it will stop alpha. Okay? So all you have to do is just put literally anything in front of you. In fact, you could almost protect yourself from alpha radiation by just wearing regular clothes. If you just cover up your skin, it'll protect your skin from the alpha. The dangerous thing with alpha is it can be dangerous if you eat something that is giving off alpha, because then it's in your body and there's no way you can protect anything of your internal organs that are emitting from that alpha radiation. So 3 types here. Alpha is the most common, by the way. So we'll start with alpha radiation in a little more detail. What it is a positively charged chunk of the nucleus. Okay, so it is always a chunk of the nucleus that is 2 protons and 2 neutrons. Right? So it is essentially equivalent to a helium-4 atom, just without any of the electrons. All right, so it is the nucleus of a helium-4. Okay, so we have 2 basic symbols for it. This is sort of looks like a fish. This is the Greek letter alpha, right? And then this right here is the symbol for helium-4. We have a mass of 4. We have 2 protons there, and it's the element helium. It just doesn't have any electrons on it, so because it's positively charged. So it's kind of what it looks like for alpha radiation. Now, when the nucleus releases an alpha particle, 2 protons and 2 neutrons basically leave the nucleus, leaving the nucleus 2 protons and 2 neutrons smaller. So it is now a different element, and we can actually kind of write down as a formula here what it turns into. So I'm going to show you how this works. Let me switch to the camera here. Okay, so here's my problem. Now, what's going to happen is I have a radium atom. Now this has 88 protons, and then it has a whole bunch of neutrons, which gives its mass up to 226. Okay, so radium. Now, what happens is it releases an alpha particle. So we are going to release a helium nucleus, which has 2 protons, and it has 4 total protons and neutrons. Its mass is 4. Okay, but what's left behind? There's going to be something left behind here. Well, if we took and we had in the nucleus 88 protons and 2 of them left, we are left with 86 protons. Okay, 86 protons is how many protons would be left in that nucleus, because 2 of them went away. If we started off with a mass of 226, and then 4 things from that mass went away, 2 protons and 2 neutrons, so we would be left with a mass of 222, or less than 226. If we look up on the periodic table, atomic number 86 is actually radon. So we would have the element now radon, Rn. Okay, that is how an alpha radiation works. This nucleus splits and we get an alpha particle, and this is what's left over. Your turn. So I want you to kind of do what I just did here. I have two radioactive isotopes, 212 radon, which has 86 protons, and 212 bismuth, which has 83 protons. Both of these will undergo alpha decay, meaning an alpha particle will come out. So I want you guys to write a little formula about what you get after this decay. So pause the video and see if you can figure these two problems out. Okay, got an answer? So first thing we do, we know that what's coming out is an alpha particle, which is a 4-2 helium. And then it's just figure out what's left over. So if we started with 86 protons and we took 2 away, now we have 84. If we started with a mass of 212 and we took 4 away, now we have 208. We look up on the periodic table what number 84 is, and I get that it is polonium, P-O, capital P, lowercase o. So we'd be left with a polonium that weighs 208. For the bismuth, okay, once again, a 4-2 helium comes out, and that's the alpha particle. And we are left with 212 minus 4, 208 again, same mass as the polonium. But this time, 83 loses 2 protons this time, so this is 81. But it's not polonium that weighs 208, it is thallium, TL. Now, the second type of radiation is beta radiation. Now, beta radiation is negatively charged, and it took a while for us to figure out what beta radiation was. We knew that it was negatively charged when kind of first dealing with radiation. Marie Curie was like, hey, we got a negatively charged thing coming out. We also were able to see that it didn't really have much of a mass, but it was pretty powerful, it could go through things, and eventually we figured out it's an electron, which doesn't make any sense because there are no electrons in the nucleus. The nucleus is only protons and neutrons. Now, we gave it the symbol. Originally, we were like, hey, there's no electrons there, so it can't be an electron. So we gave it the symbol, Greek letter beta. It's kind of like a bee with a little funny tail there. Didn't have a mass, so the mass there was 0. And then we did -1 for its protons. I'll come to the reason for that in just a minute. Okay. So where does this electron come from? It is an electron, by the way. So where does this electron come from if it comes out of the nucleus? Like, it's the nucleus that's breaking apart, but the piece that comes out is an electron, but there's no electrons there. Well, if you take an electron and a proton, one's positive, one's negative, they attract each other. They are attracted. Some scientists wondered what would happen if a proton and an electron actually were to meet, because they are attracted to each other since they move together. Well, if they come together, they actually merge and become a neutron. That is what a neutron is. A neutron is a proton and an electron that have come together. So, if we have a nucleus which has protons and neutrons in it, what happens is one of those neutrons breaks apart, turns into a proton and an electron. The electron then flies out. Since it is an electron that's not coming from the electrons of the atom, it's coming from the nucleus, we call it a beta particle. All right, so beta particle is an electron that came out of the nucleus, and it's radiation. It's got a lot of energy. So let me show you an example how this would work. If we have beta coming out, what would that element turn into? So here we have carbon-14. Carbon-14 is radioactive. It will release a beta particle. So this beta particle that it releases, I'm going to write the symbol for a beta particle. It is 0 mass, and it is basically a -1 proton. We'll come to that in just a second. And then a beta, a B with a little tail that I'm going to add on there. Okay. Now, when this electron, this beta particle, comes out, what is left over? Well, one of the neutrons is turning into a proton. So if we start with 6 protons, and then one of the neutrons turns into a proton, we'll be left with 7 protons. Okay? We actually gain a proton. Now, we also lose a neutron, so the mass doesn't change. 14 is what we start with. 14 is what we end with. Okay? So if you take a look at the numbers here, these numbers kind of make sense because 14 minus 0 makes 14. This is where it gets a little tricky. That's why we have this -1 proton. 6 minus -1 gives 7. 6 minus -1 means add 1, gives 7. Now you just got to look up what element number 7 is on the periodic table. It's nitrogen, so the symbol is capital N. Okay, your turn. I want you guys to write the beta decay equation for the following radioactive isotopes. Iodine 131, which has 53 protons, and bismuth 212, which has 83 protons. Okay, so remember, they release a beta particle, but then what is left over? Okay, got an answer? So, with this first one here, we're going to release a beta particle, so 0 mass, -1 proton, capital B with a little tail. Okay, that's my electron that gets released, my beta particle. What is left over? Well, I don't lose any mass, so 131 minus 0 is still 131. 53 minus a -1 means add 1, 54. Okay, now element number 54, I look it up on the periodic table, and I get xenon, Xe. Next one, again, releases a beta particle. What's left over? 212 minus 0 is still 212. 83 minus a -1 is 84. And number 84 on the periodic table is polonium again, discovered by Marie Curie. Now, the last kind of radiation is gamma radiation. Now, gamma radiation is not like the other two. It is not a particle that is emitted from the nucleus. It is actually energy. It's basically like light. It's very high energy light. So it doesn't have any mass. It's not even matter. So it doesn't have any mass. It's just light. It's the highest energy light there is. So it usually is accompanied by alpha or beta. So if you have a very, very energetic release of an alpha or beta, you could also have gamma coming out as well. With that energy that's released, you also get some gamma that comes out as energy. It's like big brightness that comes out. Now, the symbol for gamma radiation is the Greek letter gamma, which kind of looks like a very cursive-looking Y. It doesn't have any mass, doesn't have any protons, so it's just 0, 0 here. Now, when we do a gamma radiation problem, it's going to say it emits gamma radiation or it emits light. So uranium-238, when it decomposes, it will sometimes emit gamma radiation. So we have, first off, the gamma that gets released, the alpha particle that gets released, So it releases an alpha particle. This is a 4-2 helium. Okay. What's left behind? Well, 238 minus 4 is 234. 92 minus 2 is 90, which is thorium, TH. Okay. So thorium now also is released, and this doesn't have any mass. It doesn't have any protons. So it's just 0, 0. It's kind of tacked on to the end. Some gamma radiation. Okay, so whenever we have gamma radiation in the problem, basically just do the problem like normal and then just kind of tack on the gamma symbol at the end. That is light that's coming out, but it's not mass, it's not matter, so it's not going to really affect your equation for any of the other part of it. Okay? So summary here, 3 types of radiation. Alpha, beta, gamma. The symbols for them. Alpha, you have a 4-2 helium. It's the nucleus of a helium atom without any electrons. It has a mass of 4, and it has a charge of positive 2 because it has plus 2 protons, but it doesn't have any electrons. Okay? Beta, you have 0 mass, and it's sort of an anti-proton. It kind of has a negative proton in the symbol there, and it's the Greek letter beta. Doesn't have any mass. Technically, it has a very tiny amount of mass because it's an electron, but essentially doesn't have any mass. Okay? And its charge is -1 because it's an electron. All right. Gamma, symbol is 0, 0, Greek letter gamma. It doesn't have any mass at all because it's not matter. It doesn't have a charge because it's not matter. So those are the 3 types of radiation.